And so yeah, my name is Loïc Girois, and so I'm a first year PhD student, and so I'm working in the life science group, and more important more on the system of protein that I want to study via cryo-EM. And I'm going to talk about the nuclear physics and more especially about about the instruments at the ILL. So yeah, with precisely the fields which are explored which are explored at the ILL, and the two main instruments which are used nowadays to make the studies, which are PN1 and the FIPPS. So first of all, at the ILL, there is a lot of research about the fission processes, so which are concerning the high nucleus with a high mass, and also there is a lot of work on the characterization of exotic nuclei, and especially in the neutron-rich region, so which is shown here. And so they work on the characterization of this nuclei. So among the instruments of the ILL, so there is especially two nowadays which are operating in this field. So which are the Loïc spectrometer and the FIPPS, so which is the fission product prompt gamma ray spectrometer, which are highlighted here. And formerly there was also the GAMS, which was a very precise gamma ray spectrometer using crystals, but has been shut down a few years ago. So why to study the nuclear physics nowadays? An example of the application of the research undergone at the ILL is the checking of is in nucleosynthesis, and for example for the EV element formation, as we were talking in the discussion before, the formation of nucleus which are higher than the iron, which are bigger than iron, are basically have to use another process than fusion. And so studying the fission helps to understand and to check the models in place for these processes. And also in terms of energy, for example, for the design of new and actual and current nuclear fuel, and also predict the waste, the nuclear waste composition, and for example the heat which is generated by all the nuclear reactions which are undergoing in this fuel. So how to study this nuclei? So their production is undergone by neutron capture or by neutron-induced fission, more often at the ILL. So as was presented by Jennifer. So there's like for example the fission, and so after the splitting of the atom into two nucleus, into two separated nucleus, there's a tremendous amount of energy which is not stable, and so this nucleus needs to decrease their energy. So for this, they can use gamma rays and other nuclear processes like beta minus decay to lower their energies. And so these two reactions are more importantly studied at the ILL. And so the gamma rays are quantified from obey to a quantum law, as each nucleus has its own energy levels which are precisely quantified, and emit gamma ray when there is a transition between them. And so for to study both of the nucleus of the type of reaction which are undergone through for a nucleus to go from a very unstable state to get closer to the stability region. Mainly two instruments are used, which are the FIPPS for reaction which are very close to the fission process, and after if the isomer survives some microseconds, it can also be studied for PN1. So PN1, which is also called the Lorengen spectrometer, is an instrument where there is a target which is a fissile target, which is submitted to the high flux of neutrons and undergo neutron-induced fission, and this fission ejects some fission fragments which can be separated through a spectrometer. And so for this, there is a dipole magnet and an electric condenser which are separating the fission fragments depending of the momentum over the charge ratio for the magnet, and for the electric condenser depending of the kinetic energy over the charge ratio. And so when the fission fragments reach the detector region, already the heat mass, charge, and the kinetic energy can be found. And multiple setups of detectors can be used to see what's happening to them. And so one of the parameters which is still missing is the Z determination. So what kind of element is this fragment, even though we know already heat mass. And so for this, the use of ionization with because the energy loss of the energy loss through the ionization chamber is proportional to the Z to the Z of a fragment, and so it can be determined before to hit the foil, which is where it is stopped to be studied with the detectors. And if the nucleus is unstable, which is often the case, you can also use the gamma rays it emits, which can be studied with the germanium detectors to determine the Z. If you already know a bit the spectra of the fragment you can look for. And so for the detection, the PN1 has a great diversity of detectors available to determine fission yields. So for example, the fission yields of uranium and other fissile material using ionization chambers, for example. But also the gamma ray spectroscopy, it can also be equipped with silicium detectors to detect more on closer to the X-ray region, and also to undergo fast timing experiments. So then another instrument which is the other instrument which is important for the nuclear physics at the high level is the FIPPS, which is the fission product prompt gamma ray spectrometer, which is also functioning using thermal neutrons, which are highly collimated and pass through several collimators to have a quite homogeneous flux on the target, which is here, and which is surrounded by germanium clovers detectors, which are able to detect gamma rays, which are obtained by neutron capture experiments or by the excitation of the the fragments. So if we get closer to the target to the target setup, so what we can see here is the germanium detectors which are detecting the cameras, and also there is a particular setups which allows to detect to discriminate between the fission and the beta decay reactions, but I will go on this later. But so it's important to remind that the scintillator containing the target is here, and there is a photo multiplier tube which is also here. And so yeah, this instrument is really nice for detecting the gamma ray coincidences. So if when the several gamma rays are emitted at the same time, and so for this, what can be done is to use a gate transition. So when a gamma ray with a specific energy is detected, the concomitant of a gamma photon are recorded and can be linked to this to a transition, for example, here from Tantal. And so this can give plot like this one, where you can record the coincidence with the energy, for example, of this photon, which is around 200 kilo electron volt, which is often concomitant with the one around 40. So these are not related, by the way. Both figures are not related. And there's coincidence between two gamma rays. Also, you can also determine the angle between those two photons, which can have which can help determine the nuclear structures, the spin and parity, for example, which can influence on the energy levels of the nucleus which is studied. And so if we get another zoom on the target, which is at the middle of the FIPPS, we can see here the scintillator, which is containing the fissile targets dissolved in an organic solvent, and where the signal is because there is a lot of population of events at the same time in this instrument, and so the fact that each fragment and nuclear reaction is releasing energy and particles which are slowed down by the solvents is also able to emit light, which is which can be used to discriminate between the fission event and the beta minus decay. And so it gave fission like this, because the figures like this, well, for example, as the fission and release more energy in a short time, you can separate it from the fission events from the beta decay, which are populating a lot the gamma ray spectra if you can't separate them. And so to get an overview of what I was saying, so there is mainly two instruments to study nuclear decay at the ILL. PN1, which is an in-pile fission instrument, which is nice to study a nucleus, to study a particular nucleus which is produced by fission. but it has to where if it can survive the 2 microseconds time of flight. And also the FIPPS, which is detecting right away the information of the gamma rays and induced by the fission and the beta decay events, and which is really practical to use to make to reconstruct the excitation path of the nucleus, which is detected. And I've this is some references that I used to build this this presentation. And I want to thank you for your attention, and very thanks a lot to the people of the instruments, which helped me a lot in learning about these instruments.